Good morning, everyone. So this would be the last lecture from my side. The next lecture will be from Qualcomm. They will deliver an interesting talk on program analysis, and then the Tuesday next week would be the exam class. So usually I come to office and log in so that there wouldn't be any bandwidth issues or any disturbance. But today I am, so delivering this lecture from home. So there might be some bandwidth issues or something may happen. But let's see that it goes well. So I just thought that I will give some kind of summary on what kind of challenges that the compilers community is facing, and so those of you who are looking for research problems, you may get some ideas. So needless to say, this is not an exhaustive thing, so few things that are there in my mind. So this I kind of pulled out a few slides from a talk that I gave somewhere else. So because of that, you will see all this outline, etc. But I guess it's all right. So we started this course about architecture and and how we get performance. Just want to again quickly recap. So pretty much till let's say early 2000, the way processor manufacturers like Intel, AMD used to give performance is by coming up with excellent microarchitecture which exploits the underlying instruction level parallelism in programs. And not only that, the every next generation of processor, a new generation of processor, its clock speed will go up. Like for example, so 1995, the processor, Intel processor is running at 1.6 gigahertz. Maybe 1998, the processor may run at 1.8 or 2 gigahertz. So like that, processor manufacturers were giving performance improvement is through couple of approaches. One is by boosting the clock. So one is clock frequency. So by boosting the clock frequency. So this is one approach. Let's see why my pen is a bit thick. And second is by exploiting what is called as a instruction level parallelism. ILP stands for instruction level parallelism. That is, if there are two instructions, like for example, there is an add instruction, add R1, R2, R3, and some other add instruction, R4, R5, R6, then these two instructions will be executed in parallel because they are not dependent on each other. So what processors do is, if you recall, the basic von Neumann architecture is you fetch an instruction and you decode the instruction, and you execute the instruction. And you keep doing this again and again. So this is the basic von Neumann architecture. That means this is the semantics that is given to the programmer while respecting, like, so if in order to respect the semantics, the processor can do anything. Like for example, if the processor executes this program, one instruction, this instruction, the processor fetches this instruction, decodes it, executes it, and then it goes to the next instruction, fetches it, decodes it, and execute it. So it has some semantics. So while respecting that semantics, if the processor can do anything, like for example, like these two instructions can be executed in parallel, but on the contrary, let's say if this instruction is yeah, let's say if this, I'm just trying to get, let's say here you have register R5, then here also you have register R5, then there is a dependency from this register to this register. That is the value produced by this add instruction is consumed by the second add instruction. In such a case, the processor cannot execute these two instructions in parallel. So the processors that were manufactured at that time, they try to exploit this instruction level parallelism, and then they keep on increasing the clock frequency because the transistor sizes were going down, and because of Moore's law, the rate at which we can switch on and off a transistor, it is very high, or the switching times for transistors are going down. Because of that, the critical path lengths will go down. Because of that, the clock frequency will go up. So by using a combination of these two techniques, processor manufacturers were giving excellent performance. And these processors are called as superscalar processors. Superscalar processors. But then, so things were not quite well in the sense after 2000, what happened is the available instruction level parallelism in a program, we kind of hit a wall. Like for example, how much parallelism in a program, like for example, if you have something like x is equal to x plus 1, y is equal to y plus 1, then no, these two instructions can be, the instructions associated with these two statements can be executed in parallel. But then it's not like we never have a sequence of statements which are independent of each other. Soon we will have something like x is equal to z is equal to x star y. Right? So it's unusual to have programs to have a lot of independence from one statement to another statement, because so there is a statement, and after that something else is there, and we kind of keep so now these programs induce dependency. So the available ILP parallelism is limited. So whatever the parallelism that is available, it is used. So not much hope is there. So because of this ILP wall is there, and then there's a memory wall, the rate at which the memory is able to supply instructions to the data to the processor is not much. And then there is power wall. That is, we cannot keep increasing the frequency at which the processor runs, because the heat dissipation, the dissipated will be extremely high, and it will not be possible for us to cool the processors, for example. So this is the story, and then but till 2000, the great thing is people were just writing programs in C++, and you just rely on the compiler to automatically to translate the C++ code into machine code in such a way the ILP is maximized. Okay, so you kind of you do instruction scheduling and few other optimization passes you will have, so that so that the processor will be able to find more and more ILP in the underlying program that is being executed. So this used to be the job till early 2000, like 2002, things like that. And the programmers used to work on better algorithms. And these algorithms are all primarily, they don't worry about the kind of algorithms you learn in algorithms course, where you have one Neumann model of computing underneath. That is, you just assume that there is a single thread of execution. So when people were designing algorithms, they were designing algorithms primarily for sequential single thread of execution. That used to be the case. This is the status till early 2000. So this is the standard thing. Processor designers, they know what to do, come up with a better microarchitectures to exploit more instruction level parallelism. Compiler writer do instruction scheduling and other good and other like, for example, in order to increase instruction level parallelism, one optimization that we do is loop unrolling. So this is what the other day in the halide talk they were talking about. So when the body of the loop increases, then there will be more opportunities for instruction scheduling and more opportunities for the processor to exploit the instruction level parallelism. So yeah, and then so compiler writer, they know what to do, and programmers they design algorithms for single thread of execution. That used to be the case. But then, so since it's no longer possible to manufacture better processors, but still the amount of gates that you can pack in within a single chip, they are still increasing because of the innovation in the process technology from semiconductor physics people. So the extra transistors that are given to us, they are translated or used in different ways. Like for example, you can use a SIMD unit. SIMD unit is nothing but it's a multimedia extension unit or SIMD unit. So the SIMD unit is it's a like example, you can add a vector of 4 integers at a time. Like for example, you can have something like a of 1 to 4 is equal to b of 1 to 4 plus c of 1 to 4, something like this. This is a vector instruction. So these kind of things we can do using SIMD units. And then, so SIMD units kind of do parallelization within a thread, intra-thread parallelization. There is only single thread of computation. Within that, you are trying to parallelize operations. And then you have, right now, I think the latest Intel processors, I think they have some AVX instruction set, or I don't exactly remember the name. But the SIMD length is very large. I think maybe even 512 operations you might be able to do in parallel. And then you have to make use of the cache well, so that the number of times you reach to main memory you want to minimize, because memory is a bottleneck. So this is one optimization opportunity. So cache is another optimization opportunity. And the third optimization opportunity is across, you can have, you can split your program into multiple threads, and each thread can run on a different core. And then within a core, still ILP parallelism, instruction level parallelism, etc. is still there. So this is very important, and this is what is being talked in the halide talk. Within a core, within the single thread of execution, there is an instruction level parallelism that is available. And then there is a multimedia extensions or AVX, these vector instruction sets which are there within the core. and then there is a local cache, and then there are multiple cores are there. So multiple threads of execution are possible. So all these things, it's we have to exploit all these things in order to get good parallelization. The number of and then if you so the challenge here is, given a program, so from the algorithm designer perspective, how do I parallelize my algorithm? How do I have my algorithm so that we can better make use of simdi or cache locality? So here, in order to do this, so like, just to want to make it a few things clear. So in order to use caches, for example, tiling is one optimization loop that we use. And then in order to use SIMD, so we have something called as auto vectorization. Either you vectorize manually or compiler assisted auto vectorization. And then, for example, here, in order to exploit ILP, so you may have to do some kind of loop unrolling, things like that. And all these things, they interact with each other. And then so this across this again auto parallelization, this is task level parallelism across this task level, or you can take a loop and different iterations of the loop will execute on different cores. So again, either you rely on compiler assisted parallelization or your own approach. Just 1 minute. So I'm. Yeah. So what is, and then similarly, so if you, in order to optimize on this, it's extremely hard for the compiler to optimize. It's very hard. In order to write your algorithms or programs to work is very hard. So it's very, very challenging task. The story doesn't end there, because if you look at, like, for example, servers that are there on ADA cluster, or no, recently we bought some servers, and when we buy high-end servers with large amount of RAM, like 200 GB of RAM, 300 GB of RAM, and so usually the system will have multiple sockets, and each socket will have a multi-core processor, and the memory is distributed, and so the time taken by a core to access memory that is present in a non-local memory module is higher. So optimizing your algorithm, at an algorithmic level there are problems, and there are at a compiler level there are problems. So a whole bunch of challenges are here when we go from uniform memory access model to non-uniform memory access model, where there are multiple sockets, multiple processors are there, and memory is distributed. And then you all know about GPUs. GPUs are the bread and butter for, like for gaming and these days machine learning. And the architecture of GPUs is extremely very, very different from the architecture of your multi-core systems or multi-processor systems. So an algorithm which runs fantastic for a multi-core, multi-processor system, it may be completely bad for GPU, because the underlying architectural model for GPU is very different. And then if you take a modern system, you will have a NUMA system, and then you will have multiple GPUs, and then some other accelerators, an FPGA, a tensor processing unit. So there are so many DSP units. Like, for example, in the Halide talk, they were talking about a processor, and then they have a Qualcomm's accelerator that is present on the same system. So they want to optimize the image processing algorithms for the accelerator. The way you optimize an image processing algorithm for a GPU is very different from the way you want to optimize it for a multi-core machine versus a tensor processing unit versus the FPGA. Yeah, so And the story doesn't end there because, we have a large cluster of such systems. They are connected through different kinds of backbones, and there is a storage area network. And so the underlying architecture, it's a extremely complex architecture. It's not the you will not be programming. No, when you go to industry, you may not be programming for your for your laptop. Even your laptop itself is very sophisticated, but if you go and look at real systems are extremely complicated. And in order to exploit the full power of this underlying architecture, you have to use many computational frameworks are provided. Like for pthreads are used for exploiting no for multi-threaded execution. OpenMP is automatic. OpenMP also facilitates multi-threaded execution. And then there is OpenCL. CUDA is for GPUs, and then remote procedure calls is for distributed systems. Similarly, MPA is for distributed systems. MapReduce, Spark. It keeps going on. So there are so many computational frameworks. So given a problem, picking the right computational framework to solve it, and then learning about that computational framework, and then getting the best out of that computational framework, all this is a very hard task. So the current challenge for compilers is to you write your program in C++. That's what you learn in college. Okay, everyone is taught C++, and you learn Python. And then we want to give that program to a compiler, and we expect the compiler to do some magic and to use the underlying architecture to the fullest. But this is an extremely hard problem. It's a very, very non-trivial problem. So with so much efforts, with decades of research, the progress that is being made is very minuscule. So, like for example, even if you take in the last talk, if you recall, so there is an image processing algorithm. You try to express that image processing algorithm using the Halide domain-specific language, and then there are multiple optimization schedules that you can have. Like for example, unroll the loop, tile the loop, and then vectorize operations. And you can do it in different orders. So you can use different loop unroll factors, different tiling factors. So there are so many schedules that are possible to execute a given program. So it's not possible for us to figure out what is the among all these tens of thousands or infinitely many schedules, what is the best schedule that is available out there. So one approach is through analytical modeling techniques, but analytical modeling techniques are very hard because systems are complex. Coming up with a decent analytical model which makes sense is hard. The second approach is you kind of apply a heuristic search technique. So the heuristic search technique is, like in your AI course, you study A star algorithm, genetic algorithms, things like that. You try to use heuristic search techniques in order to find a good schedule. All this doesn't make sense if you for many programs. But let's say if you are porting an image processing library to a particular architecture, then that particular image processing library can be tuned by using these heuristic search techniques so that you choose the parameters which are best for that architecture. This is what is called as an auto-tuning technique. Sorry. This is called as an auto-tuning technique. So this approach may not work for everything, but for at least for libraries, which are frequently used, when you are porting them to a new architecture, to a new machine, you can use these auto tuning techniques so that you get the best performance out for that particular library. So here is the question. So, like for example, can machine learning help? So among the millions of schedules that are available out there, so can you kind of build a classifier or something like that, which, like for example, takes a C program and two schedules, and the classifier should be able to say between these two schedules, the first classifier, the first schedule is better than the second schedule. The particular example that you are seeing on the screen, it is with respect to what is called as a compiler phase sequencing problem. So let's say there is a C program and there is an optimization. You want to apply loop unrolling, or you want to apply inlining, or some kind of optimization. And this classifier should be able to say yes or no, telling no, for example, whether this optimization is useful for the C program or not. So yeah, but so here comes the challenge though. If you want to apply machine
The
learning,
slides are not visible.
slides are not visible.
Yes, sir. Since the last 5-10 minutes, I think.
I'm really sorry. You're all okay. Let me do this. Missed out on many important things. Then, wait. What is the last thing you saw? Did you see this one?
Sir, I
This one you
think we
have
were
seen.
just above this slide. Yes, we were here. You were explaining SIMD and those things.
Oh, okay. So I think you understood the thing, but I quickly want to show the slides also so that it becomes. So what we are saying is we start with a single processor system. So this is where we start with a single a system with only one core, and then we go with a system with multiple cores. Each core will have its own SIMD unit, and it has its cache. And so in order to get good performance, you need to know how to use the cores well, that exploit instructional parallelism within a core, SIMD units, caches, so on and so forth. And then when we go to the next level, then what happens is you can have multiple cores within the system, and you can have multiple memory modules. Some memory modules could be local to a core, and some other memory modules may be non-local to a core. And again, so optimizing here becomes a challenge, because the performance depends on whether the thread, when a thread is accessing data, the performance depends upon whether the data is present locally, or in the local memory module, or in the non-local memory module, right? And then we have GPUs. So GPUs have a different architecture, and it's so you have to think completely about your algorithm and the way you write the code if you want to use GPUs. And in modern systems, we have a NUMA system, multiple GPUs, multiple accelerators, and we want to use all this underlying architecture. And and then we expand. So we just don't have one such machine. We have a huge collection of such machines which are connected by a RDMA or InfiniBand network and a storage area network. And so given such a cluster, how do we go about optimizing our program for such an underlying architecture? And there are varied computational frameworks for all these things, but so if you have written a code in OpenMP, and if you want to port it to pthreads, it will take quite a bit of time. So moving from one framework to another framework is not easy, and you have to use a combination of frameworks. For example, you may want to use procedure calls and OpenMP together, or MPI plus OpenMP together. MPI helps in distributed programming, OpenMP helps in multi-threaded programming, so on and so forth. So the landscape, the programming, the computational frameworks that are available out there, they are varied, and learning them, mastering them is takes time, and it's very expensive process. So what we are hoping for is, like write a C program and uh, magically our compiler will do everything for us. Uh, but then there is a problem because compiler has to do a lot of work in terms of analysis and transformation. There are many possible schedules that the compiler can use, and in the absence of a good cost model, which is very difficult to get because of the complexity of the underlying architecture, it will be a hard job for the compiler to generate optimal target code which uses the underlying architecture well. So one approach is to use the heuristic search techniques. Like for example, in the Halide, you write the program and then so there are you can put together different schedules by using unroll, tile, vectorize, these kinds of operations, and you kind of apply some kind of a search algorithm to find an optimal schedule. But the problem there is it kind of works all right, for it's a reasonable strategy to do when you are working with libraries, because you want to put a new library, OpenCV library or some library to a new architecture. So you are willing to, let's say, spend 1 week of time to kind of find out for the 100 different programs that are present in the library, what is the best schedule for each one of them. But it's still an expensive process. But it's still a viable approach, though. So the question is, in this context, can we use machine learning based techniques in order to figure out the best schedule? So in the last class, those again, so Qualcomm people are trying to use machine learning to figure out what is an optimal schedule or suboptimal schedule or near optimal schedule for a given program written in Halide. So it is an interesting, those of you who are looking at application of machine learning and systems, this is application of machine learning in systems. So this is an interesting problem. So in Halide, when you look at the schedules, Halide provides a way for writing the schedules. Among the different schedules which we can use, an important research problem there is, can we use a good ML-based approach to uh, to kind of narrow down on, let's say, if there are 1,000 schedules that are you start with, on the space of 1,000 schedules, using ML-based approach, if you can reduce them to 10 schedules, then you can try out those 10 schedules and see which one works out. So this is a very interesting research problem which you can pursue either for your for your research project. It would be a fun problem to work on. And but the problem in applying machine learning based approaches to uh, in the context of compilers is this. In the context of computer vision, uh, so there is a natural, there's an image and the raw image you give it to a CNN. In before CNNs, all these things are there. There is a 15-20 years of research on what is the best feature vector representation for an image. So many features, hog features, shift features, things like that are there. So after CNNs came, there is these features are automatically extracted from the raw image. Same thing with NLP. So in the space of NLP, so before ML based techniques came, so there is a lot of work on which uses linguistics, theory of linguistics, in order to model the underlying problem and things like that. But then with the advent of LSTM networks and other things, and large amount of data that is available, so people are able to automatically encode uh, extract language features. Okay, you might be in the NLP course, you might be learning some embeddings of words and embeddings of sentences, etc. Maybe. Now, when we come to context of programs where we want to give a program as an input to a machine learning model, a program is a sequence of characters. And how do you give a sequence of characters as an input to a program? Sorry, to a machine learning model. So, what is a good feature vector representation for a program? And so here comes tremendous amount of research opportunities. Like for example, there are what are called as static program features. In the static program features, like you kind of count, the number of the average number of instructions per basic block, the average, what is the ratio of load store instructions with respect to compute instructions. Like that, you can come up with many features. So, what is a very structured program? You kind of map it into a feature vector by considering these attributes, the number of fee functions present in the program, things like that. So these are the static features, and we can use these static features to represent a program. And then dynamic features are those which we get when we actually execute the program. Like for example, when we execute the program, it is possible for us to measure the number of instructions executed per clock cycle. That is what is called as a CPI. And you can measure the L1 cache misses, L2 cache misses. These are the dynamic features of the program. So once we come up with a feature vector representation for the program, then we can use uh, any of the machine learning models. And unfortunately, but then there is another problem, that is what is called as a sample complexity. If you want to train a machine learning model in vision, so like you let's say for face detection problem, so if you want to get no training data, so in the class of 100 students, each one of you take out your phone and you take a picture of each other, immediately you have a sample training data of at least 200 to 300 images. But then, if you want to collect training for data for training programs, it's extremely hard because writing programs is not as easy as taking pictures. So this is a very hard problem. Uh, So there is a lot of research happening where people are, and also this what static features should be used, what dynamic features should we use, and then there is in the program there is a rich control flow graph structure, and we are when we construct a linear vector out of this program, we are dumping out all the control flow information in the program and coming up with static features. So there are plethora of problems here in applying machine learning in the context of programming languages. So, but in the last few years, uh, there is a little bit of success in applying techniques which are used in NLP to programming languages. There is a little bit of success, but this whole area is completely open. And also, there is one more interesting thing. Should you extract feature vector from the source program, or should you extract the feature vector from LLVM IR? Is a nice question. And if you want to, if you decide to extract the features from LLVM IR, should you extract the features before applying optimizations or after applying optimizations? Uh, very interesting questions are here. And so if anyone is interested in working in this space, so you can just drop me a note, we can discuss. And but I have to warn you though, the complexity of working in this space is very high, because when you work with no NLP kind of stuff, the data sets, and it's all, you essentially end up working using some Python libraries, etc. But when you're working at the compilers, applying these techniques in the context of compilers, we should have the knowledge to go and hack the compiler, extract the features, represent things, etc. So it's the challenge, the complexity of the problems here are much more when compared to the NLP space. I'm not saying NLP is not hard, it has its own challenges, but the kind of challenges that you face here are a bit different from the challenges which you see in NLP space. Like, for example, a couple of students in this class, they are working on one problem in this space, but in order to get something, in order to make some progress, we have to hack the LLVM compiler, write a pass on it, and it takes a good amount of time to get a hang of it. So anyway, I think, yeah, this is what. So this is about machine learning in the context of compilers, and then domain-specific languages. Uh, so, so as I said, like you people, we still want to write programs in C, C++, Java, Python, JavaScript, whatnot, and then we expect compilers to map them to multi-core CPUs, many-core GPUs, CPU-GPU combinations, FPGAs, things like. But all the language abstractions which are designed on the left-hand side, they are they are designed keeping in mind von Neumann sequential architecture. So in order to, but the architectures on the right, they are very different from the von Neumann sequential architecture. So there is a huge gap in the source language specification and the target architectural features. So bridging this gap is a real challenge for compilers. So, and there is huge amount of work that happened over the past 30 to 40 years in the context of high performance computing. So things like polyhedral compilation, etc. They were all trying to do this only, trying to bridge this gap, but the success is very small. But let's take matrix addition problem. So let's say you have a domain-specific language for matrix computations, like for example, MATLAB. So you will say matrix A, B, C, and you want to add two matrices. You say A is equal to B plus C. So the code that is there on the left-hand side, it is extremely small code to write, and it also provides a lot of information to the compiler about the structure of computations that are happening there. But if you go see on the right hand side, where you have a two-dimensional for loop which is written in C in order to do the same computation, the compiler, it's hard for the compiler to figure out that you are trying to do a matrix addition problem. There's a two-dimensional loop and there is an instruction, there's a statement. So the compiler has to reverse engineer what you have to do. So if you stick to the left-hand side, it helps the programmers because they will write less code, programmer productivity is improved, and from compiler's perspective, the rich information that is there in the program is preserved. On the right-hand side, the programmer productivity went down, number one. Number two, from the compiler perspective, the analysis required to extract any kind of information from it is humongous. So so for example, so towards this, what people are working on is, instead of working on general purpose programming languages, parallel, so people are trying to design domain specific language target like image processing, maybe for some other domains, I don't know. So for example, here, I will not go through all this stuff, but here you take an image, and so this is what is called as an image processing pipeline. So in the stage IX, you kind of apply some kind of filter on the image, and in stage IY, you kind of apply some other filter on it. So like that, the image moves through this directed acyclic graph of stages, and at every stage, you do what is called as either a point-wise computation or a stencil computation. If you write this code, if you write a C program for this code, you will have at least 20 loops, if not 20 loops, at least 10 loops will be there in your program. And for the compiler to completely understand all these 10 loops and understand that this is what you are trying to do, it's complete, no, it doesn't make sense, because the rich information that is there, you are flattening it out and you are expecting the compiler to reconstruct that information, which is a bad idea. And also from the programmer perspective, it is hard for him not to write lots of code. And if he has to manually, paralyze it, okay, then there are so many loops. So what tiling strategy to use, what scheduler to use, what loop control factor to use, how to vectorize it. It's completely difficult for an ordinary programmer or even a very experienced programmer to do it. So instead, so in our Flowpix is a language which we design in IIIT. It's a Scala-based language. So if you see, this whole computation is nicely expressed using 15 statements. There are 15 stages associated with every stage. We just have one statement. And so this is a Scala-based DSL code. So with this, the programmer productivity is very good. This whole structure of the computation is preserved. And then the compiler, instead of spending humongous amount of work in analysis, it already knows the structure of the computation. It can put its energy in coming up with a good schedule. So Flowpix DSL compiler, so right now it targets an FPGA. So it takes a DSL program and it generates a target system which can, a target architecture which can run on an FPGA. And so Flowpix is like kind of, it's equivalent to Halide. We were, but ours is a Scala-based system, a Scala-based DSL. Halide is a C++-based DSL. Of course, our Flowpix DSL, it doesn't have a backend targeting CPUs, GPUs, etc. So because of that, it's not of much appeal to regular processors, but for accelerators, it's very good. So let's see what else we have. Yeah. And in the same context, right now, like machine learning, so you have your machine learning models, already pre-trained models for object detection, segmentation, or many other vision tasks, speech recognition tasks, etc. So once we have these models, deploying them on edge devices is a challenging task because they have low resources in terms of memory, compute, power, etc. And not only that, if you want to generate uh, custom accelerators which can run these inference, these machine learning models fast, then designing optimal accelerators for these machine learning models, it's a very, very challenging task. So again, so in our group, in IIIT, so we have a framework called FlowCNN, where it can take a TensorFlow model, a pre-trained TensorFlow model, CNN model, and it can automatically synthesize an accelerator which can run that model very fast. It gives high throughput but consumes very, very low power. So to conclude, what I would say is I would like to, so number one is there is a very good amount of research happening in how to apply machine learning techniques in the context of compilers to for a variety of tasks, for generating better schedules in less time. That is one example. And like compiler phase optimization problem, things like that. So that is one broad area. The challenges there are, so earlier coming up with a good feature vector representation for programs, it used to be a big challenge. But now people are trying to retarget NLP models on the programs and see how they are working. Um, Of course, there is another problem there, that is sample complexity. That is, the number of available programs for training is limited. So how do we solve that problem? That's a question. Uh, so that's one big area of research which we can look into. Second area of research is in DSLs. There are many DSLs that are coming out. People figured out it is hard to uh, come up with programs which are come up with compilers which does everything magically. So you just write C program and everything works fantastic. It's not going to happen. So people are encouraging coming up with DSLs for different domains. That makes the job of the programmer also easy, because from the productivity perspective, from the compiler writer perspective, the structure of the computation is retained. Since the structure of the computation is retained, the compiler can spend more time on transformation rather than on analysis. That is the second area of research, which is very, very promising area of research. The third area of research is broadly on AI and ML, deploying AI ML models on the edge and on the data centers also. Like, for example, if you take on the edge, power is a problem. You want to do inference very fast while consuming less power, and environment is a very resource constrained environment. And if you go to data center, like for example, many data centers, they are betting on FPGAs to do, because in data centers again power is a problem. So they want to achieve high throughput using low power. So there is a lot of again effort is put from company, from big such as Google, Microsoft, Facebook, on investing in FPGAs in their data centers. So so how do we translate these CNN models, these ML models onto this, so that these target architectures are used well, is a third area of research. So with this, I conclude today's lecture. I'm kind of a little bit all over the place, but it's all right, I guess. So I think that's all I have, but I would like you all to attend the Thursday session. It will be very good, and it will be the last lecture. So yeah, so that's all I have. Thank you. And if you would like to talk to me about any of these research problems separately, please feel free to drop me an email. We can catch up. Okay, so that's all I have for you today.